the cross section of the Gulf Stream, and we were discussing about the slope of the isothickness of and now let's see. These are the currents associated to this, and let's now talk about the thermal and the wind relationship. The thermal wind relationship is. Do I have anything? No. I have the finger. So thermal wind relationship is the geostrophic method, which tells us that in the case of the vertically homogeneous fluid, of the barotropic fluid, the vertical shear, the vertical change, the vertical gradient of horizontal velocity is 0. So that means the vertical velocity doesn't change with depth. In the case, however, in the case where we have the horizontal gradient of density, in that case we will have the changes, vertical shear, vertical changes of the horizontal velocity. How do we explain this? If you look at the two water columns, and we have with different density where rho A is and rho B, where rho A is larger than rho B. That means that the water column A is lower than the water column B. As I told you before, that the higher is the density, the lower is the water column. So, in that case, the pressure gradient force is acting from B to A. Good, thank you. So the pressure gradient force is acting from B to A, and as a consequence of that, we have this the velocity which is going into the geostrophic velocity going into the blackboard, into the board, and it's proportional, obviously, to the horizontal pressure gradient due to the difference in density. And so at this point here, we have contribution of the sea level to the water column above this is higher than the water column above it, and although the density here is lower than here, the pressure gradient force is the pressure is larger here than here. This is something. This is how we can obtain the surface flow as a function of the sea level slope. Okay. If you go further down, if we integrate the pressure here is simply the weight of the water column from this height up to here, from this depth to here, and this height weight of this water column, we have to compare to the weight of the water column here. And although the differences between the two pressure gradient, between two pressure diminishes because the influence of the sea surface height is lower and weaker. Therefore, as a consequence of that, the pressure gradient force is lower here than there, and consequently also the surface, the geostrophic flow is weaker. Further we go down, smaller are the differences in the pressure between these two water columns, because we are adding the pressure, the density has more and more influence with respect to the sea surface height. If you go further down, we can imagine that there would be a depth at which finally the density plays a major role with respect to the sea level height. So if we have horizontal gradient of density, this would end up finally also in changing the direction of the geostrophic flow due to the changing of the of the changing of the orientation of the pressure gradient force. So this is the and so we finally can end up where there is no pressure gradient force, since the total mass and B and A are the same. So the weight of the water column on the two sides, on the two water column is the same. So this is how this is the explanation or a description, a qualitative description of the thermal wind relationship. Now we can assume that the density varies continuously. We measure density, where is not the red line. The slope down to the right means that flow increases into the page with the height. Okay. We assume or measure that velocity is 0 at depth 3. Therefore, the pressure contour P3 must be flat. Exactly where we arrived in a previous graph, where the weight of the water column above a certain depth becomes equal, and in that case, the flow will start going back the other way out of the page. So this is the yes.
About the previous slide, it's usually a little bit confusing. You said
yes.
The density is linearly related to pressure.
The density is yes.
And if you check the height, if you see an image like this and there is nothing indicating salinity, how do you tell that this row here is greater than this row here?
I didn't understand. Can you repeat this?
Like,
what about
if you see a cross like this and nothing is indicating the salinity, how do you tell that the density here is greater than here?
Oh, but we don't talk about the salinity here. We talk about the density itself. Okay.
So in that case, how is density rho at 1A greater than the one at B?
Oh, we assume that the rho at A is larger than rho at B. Obviously, we know that since the density is a function of temperature and salinity, in order to have a larger density here, we have to have larger salinity or lower temperature, or larger salinity and also the lower temperature, and here on the opposite, So this is how, and these are our assumption. Our assumption is that rho A is larger than rho B.
So it would always be given. The assumption will always be given in case of plots like this.
Yes, or you can do your calculations and find the density between the two different points at a different depth, and then do your calculations of the vertical shear or the changes of the horizontal density with depth. Because if you can see from here with these qualitative considerations, the horizontal the vertical shear, so that means the vertical gradient of the horizontal velocity is proportional to the difference of density between the two columns, two places in the ocean. And this is how you can see that if the density rho A is equal to rho B, you can see that there will be no changes. There will be no changes of the horizontal velocity with depth, because you will have always here the differences in the water column weight. About here is this one, so the difference is due to this part here. And if you are here, again you will have the differences due to this part of the water column, independently of density, because density in assuming that rho A is equal to rho B, there will be no changes, no vertical changes of the horizontal velocity. So this is the barotropic fluid, barotropic situation in the world ocean. So the thermal relationship simply says that if there is no changes, horizontal changes in temperature, there will be no vertical shear in the horizontal velocity. Okay? Obviously, this is if we assume that density varies continuously, we measure density at the red line. The slope down to the right means that flow increases into the page with depth. We assumed or measured that velocity is, say, 0 at depth 3. Okay, where is depth 3 is here. Therefore, the pressure contour must be flat. So you can see the pressure and below the level 3, the flow should start going back the other way out of the page. So you can see that although looking at the sea surface, we have the geostrophic flow, which is a certain direction and certain magnitude. Due to the horizontal distribution of water masses within the water column, we can have the opposite flow in the deeper layers. So these are the limits of our measurements of the satellite from the satellite of the sea surface height. Because we can say, okay, the surface we have a geostrophic flow such and such, but we don't know what is happening in the water column. We don't know what is the distribution, density distribution within the water column. We don't know how big is the vertical shear, how big are the gradients, vertical gradients of the horizontal velocity. Okay, so pressure gradient force is calculated as the difference of pressure between the two stations at a given depth. So pressure at the station at a given depth, at the same height, at the same depth, which are flat surfaces relative to the geoid. If the velocity is known at a given depth, then the pressure gradient force at that depth is also known from geostrophy. Or vice versa. If we know the pressure gradient force, we know geostrophic flow. And from the measured density profiles at two stations, we can calculate how the pressure gradient force changes with depth, which tells us the velocity changes with depth, always from the thermal wind relationship. Okay? Using the known velocity so by knowing the vertical distribution of the pressure gradient force, we cannot obtain the absolute velocity. We can obtain only the vertical shear, the vertical changes of the horizontal velocity. Only in the case we know the velocity from a certain depth, which is the reference level, we call it reference velocity, and knowing how velocity changes with depth, we can compute velocity at every depth. So, from the thermal wind relationship, we are able only to determine the vertical shear. We are not able to determine the absolute velocity. In order to obtain the absolute velocity at all levels, we have to know, at least at one level, we have to know the velocity. So, or we measure it, or we do some other way of assuming what is the velocity at a certain depth. Okay, so to get the change in pressure gradient force from depth 1 to 2, get the mass of water of both profiles between depths and 1 and 2. So we have to get the density between the two depths. Historically, we use the specific volume anomaly, which is this thing here, the specific anomaly at 35 parts per thousand at zero temperature and pressure P, where alpha is 1 over P is specific volume. Then choosing or measuring or guessing the reference velocity at, say, depth 1 and compute velocity at depth 2. So we can do the, as what I told you before, we can do the determining the absolute velocity by knowing the velocity at a certain depth. I won't go through this thing. If somebody of you wants to go through this and want to present this at the exam, we can. You can do this, take this as an exam exercise and present this instead of responding to my question. Think about it. Okay, so, but you can find this in a Stewart book very, very detailedly explained. So if you want, you just tell me and prepare this exercise in 10-minute presentation. Tell me, you explain to all of us what is the dynamic geopotential anomaly and dynamic height calculations, and then you present this, and this will be your exam. I promise I won't ask you anything else. Okay? So, oh, sorry. This is now we are in the problem of reference velocity. We have to know. We have to determine the reference velocity, or we assume where the velocity is zero, or as it used to be called the level of no motion. Level of motion is simply assuming that at a certain depth the water doesn't move, so the velocity is zero. This is a very crude assumption and old-fashioned one, and so it's not very reliable. It's better, obviously, to observe and determine through external means, use of tracers, mass balance, and so on, a good guess of the velocity at some depth and level of known motion instead of level of no motion. So what can be done is simply do the measurements at a certain depth and do the average over long term. Why over long term? Because we are talking about the geostrophic velocity. We know that the geostrophic assumption is valid if we are talking about the time scales on the order of several days, or a week, or a month, also a better month. And then you do your measurements, do the average over the entire period, and this you take this as a known motion, and you have the level of known motion, and then you calculate the vertical shear from that very specific level up to the surface and below. This is how we can use this to study deep circulation. Why deep circulation? Because if you are talking about the surface layer, in a surface layer, the geostrophic assumption on it's quite a tricky assumption, because the wind influence is very important there. So in the first 1,000 meters, you have to take into consideration the influence of wind. But if you go to the deep circulation, then the geostrophic flow could be a rather good approximation. Okay? This is again the Gulf Stream density, and this is the specific volume anomaly which has been calculated from the formula some of you will present to us if you are interested in. You have a dynamic height, what is another parameter which is important in determining the geostrophic flow. And geostrophic velocity, finally, this is the geostrophic velocity, which you can see at the surface goes up to 100 centimeters per second, 1 meter, and then decreases very fastly. And you can see that there is a strong horizontal shear, vertical shear of the horizontal velocity. Why? Because you have, if you look at here, these are the density. These are the densities, and you can see that the horizontal density gradient is non-zero. If the horizontal density gradient is non-zero, as we have seen before from the thermal wind relationship, there is the vertical shear. There are vertical changes of the horizontal velocity, which is especially strong here. For example, here you have a 26.5, and here you have a 27.5. So you have a strong gradient of density, which results in a vertical shear. further you go down, the isopycnas are more or less horizontal, so the horizontal gradient of density is weaker, and therefore the vertical gradient of the horizontal velocity is weaker. So you can see here in a play the thermal wind relationship, which is applied in this specific case to the Gulf Stream. Here is something what is called steric height, which are similar to the sea surface height, which steric height depends on the specific volume. The higher is the specific volume, the higher is the sea surface, the steric height. And if you compare this thing here, where you can see again subtropical gyre in Atlantic Ocean. If you compare this with the sea surface height, you can see that they are very similar. They show the similar features. Therefore, what I told you before, the density or the specific volume, the larger is the specific volume, the larger is water column. So the sea level is very expresses what is happening in the water column inside, because the higher is the temperature, the higher is the density, the lower is the water column, and vice versa, or the specific volume, which is inverse of the water density. Similar thing is in a Pacific. Again, the subtropical cyclonic, anticyclonic or cyclonic gyres, northern southern hemisphere. Looking at the sea level, you can see again these very huge bumps at the sea surface, which reflects in a geostrophic flow, leaving the bump on its left. Okay, so here you have the anticyclonic circulation. You're leaving the bump on its right, and here is on its left. And also you can see that these are the areas where you have a strong current, where you have the strong shear, where you have a strong slope of the sea level on both northern and southern hemisphere. The similar thing is in Indian Ocean. You can see how the oceans are really have the same features, and they are very similar to each other. So there are some mechanisms which are determining the presence or maintaining these large-scale features in the world ocean, and what makes them present in both northern and southern hemisphere and in all the oceans. We'll see later what is the reason for that. This is just another thing, just the North Atlantic. Again, this subtropical anticyclone and so forth. Okay, so this is as far as the geostrophy is concerned. So geostrophy is practically a steady solution of the equations of motion. Okay, so and we have shown, and we will be showing even more than that, how this geostrophic flow is a good approximation of the long term of the steady flow in the world ocean. But now we have to talk about the wind influence, which is another important mechanism which determines the flow. So we will be talking about the response of the upper ocean to winds. Upper ocean, obviously, because the direct influence of the wind to the deeper layers is not present at all. It is present, but indirect, and we will see later how it is present even in deeper layers. So it's not that so here are important concepts of the wind influence, which will be analyzed in more details later on. So, first of all, changes in wind stress produce transient oscillations in the ocean, which are called inertial currents. You remember I showed you a few lectures before the inertial flow, the inertial currents, but they are generated by the wind only in the situation when the wind stops or when the wind changes a lot with time. And so because if you remember the equation which has as a solution inertial currents are having the time dependent, are having the acceleration on one hand, and you have the Coriolis component, and you don't have any forcing. So that means that there are free oscillations which appear only when the wind stops. So inertial currents are, as we have seen before, are very common in the ocean. They can be easily seen by from the experimental data, and the period of the currents is 2 pi over f, where f is the Coriolis parameter, and so that means that at our latitude the period of these oscillations is around 17 hours, so a little bit less than 24 than the daily tides. And on the other hand, so we have these are these time-dependent or transient oscillation, but steady winds produce a thin boundary layer, which is called also the Ekman layer at the top of the ocean. And this Ekman layer is on the order of several hundreds of meters, where we have a direct influence of the wind. Direct influence of the friction due to the different velocities of the air and sea. So if we have a horizontal, if we have the vertical shear between the air and the sea, that in that case we have a strong friction, but that means that the Ekman boundary layer also exists in the bottom of the ocean and also the atmosphere. In the bottom of the ocean it exists because, again, of the strong changes of the horizontal velocity with depth close to the bottom. So we call this as the bottom Ekman layer. And Ekman layer in the atmosphere above the sea surface is also called the planetary boundary layer. Somebody tell me how big is the boundary layer in the atmosphere? You have an idea?
1 kilometer?
Something like that. Is it?
1.
Okay. And in the ocean, it's on the order of from 10 to 100 meters. So it's an order of magnitude larger. So the surface Ekman layer is on the order of several hundreds of meters in the ocean, and at the bottom is around 100 meters. The Ekman layer at the sea surface has the following characteristics. These are the main characteristics of the surface Ekman layer. First of all, the direction is 45 degrees to the right wind looking down in the northern hemisphere. So if you have wind blowing over the ocean, the current will not be parallel to the wind velocity. It will be 45 degrees to the right with respect to the wind velocity, and surface speed of the current is 1 to 2.5% of the wind speed, depending on latitude. So if you have, we know that the typical wind speed is on the order of 10 meters, right, more or less. So if you take a 2% of 10 meters, so it's 1,000, 2% of 1,000 is around 20 centimeters per second, right? 10 to 20 centimeters per second is the wind-induced surface speed in the ocean. And here is the depth of the Ekman layer is 40 to 300 meters, depending obviously on latitude and wind velocity. We'll see how it depends on latitude and wind velocity. And here are the careful measurements of currents near the system show that the inertial oscillations are the largest component of the current in the mixed layer. Although they are the largest component of the current in the mixed layer, they have a relatively weak importance on the general circulation of the ocean, because they are transient. They appear only in a specific situation, and due to the friction they die down very quickly. The flow is nearly independent of depth within the mixed layer of these inertial oscillations. And here is the third thing what we already have told. Okay, so now we have started at 11, right? Surface drifters tend to drift parallel to lines of constant atmospheric pressure at the surface. This is consistent with Ekman theory. The flow average over many inertial periods is almost exactly that calculated from Ekman's theory. Okay, let's see first this. Surface drifters tend to drift parallel to lines of constant atmospheric pressure. The lines of Ekman constant atmospheric pressure, we know that the geostrophic wind is parallel to the isobars, but in the atmosphere, both in the atmosphere and the ocean, there is no perfect geostrophic balance, because we have to take into consideration also the friction. So that means that the velocities are not perfectly parallel to isobars, but they are slightly deflected from the isobars to the left. They are deflected toward the lower pressure in the atmosphere, and surface drifters are passive drifters. We stay at the surface, and they are moved by the influence of the wind. If the wind is so the surface drifters tend to drift parallel to lines. They are moving with the current. Since they are moving with the current, and the current is 45 degrees with the wind, and the wind is slightly deflected or being parallel to isobars, that means that the surface drifters are parallel. Their movement is parallel to the lines of isobaric surfaces. Okay, so if you let me try. Do I have the? Oh, here it is. If these are isobars, P plus 1, P plus 2. So what is happening is that in the case of a perfect geostrophy, we will have this thing here. Okay, but due to the is it okay? This is geostrophy. Is it right? Leaving on the northern hemisphere? No. Am I right or no? Wrong?
It's okay.
Huh?
I think it's right.
Right. Okay. So due to the friction, the real vector will be okay. So we have the pressure gradient force is this way, and the Coriolis force is that way, right? So due to friction, the real vector, the real current vector will be deflected to the left. Okay. And it says here that the drifters are moving parallel to the isobars, so that means that they will be moving parallel in this way. Okay. So these are the movement of the drifters. And this is exactly consistent with Ekman theory, because this is the real wind. And the drifters, whose movement is determined by the flow, will be moving to the right-hand side with respect to the wind. Okay, so the drifters, surface drifters, will move parallel to lines of constant atmospheric pressure at the sea surface, due to the which is consistent with Ekman theory, but simply because we have to take into consideration also the friction in the real ocean. Another important stuff as far as the influence of the wind is concerned is that the total transport, mass transport in the surface is 90 degrees with respect to the wind in the northern hemisphere, the total mass transport. So in the surface, very surface flow induced by the wind is 45 degrees with respect to the wind. But if you do the vertical integral over the mass integral from the surface to the bottom of the Ekman layer, that means in the first 300 meters, the total mass transport will be proportional to the wind, and it will be 90 degrees to the right with respect to the wind. Okay, so these are two important things when we will be talking a lot about that later on, when we will try to explain the transport in the world ocean by steady winds and the maintenance of the large gyres in the world ocean. Spatial variability of Ekman transport due to spatial variability of winds over distances of hundreds of kilometers and days lead to convergence or divergence of the water transport. What that means? Let me just put it here. What that means in a if we have spatial variability of Ekman transport. So if we have the Ekman transport here, this way, and here we have that way, this should lead to convergence or the divergence in the transport. Or we can let's think about this thing in another way. If we have the wind blowing this way here and that way here, and here the wind is stronger than there, we said that at the northern hemisphere the Ekman transport, the mass transport, is to the right with respect at right angle, and to the right with respect to the wind speed, to the wind. And here it will be, the transport will be lower, because the Ekman transport is proportional to the wind speed. The result of this is that we will have here divergence. Here there will be more transport than there. So here we will be having the loss of the water volume, because due to this stronger wind here, there will be more transport here than here. Therefore, somehow there will be losing of the water volume here. So this water volume obviously has somehow to be substituted from the water volume in some other parts. But this anyhow causes the divergence in this specific case. We can imagine the another situation where we have a similar situation where the wind is again parallel, but here we have the larger wind velocity with respect to this one, and here in this area here we have the convergence. Okay, and this convergence or divergence due to the spatial variability of winds over distances of several hundreds of kilometers could lead to convergence and divergence. And you will see later what are the consequences of this. There is another thing which is very important, is that winds blowing toward the equator along the west coast of continents produces upwelling along the coast. This leads to cold productive waters within about 100 meters from the shore. If you have the wind, if you have the coast, if this is coast, and if we, on the northern hemisphere, if the wind is blowing this direction, this is the wind. What's happening? It happens that there is the Ekman transport to the right hand side with respect to the wind. But here you have the coast, so you are taking away the water from the coast. Okay. And that means that there is a divergence, and this lack of water which has been taken away from the coast has somehow to be compensated by some other water, because we cannot lose the volume. The volume continuity equation requests that there is always whatever you lose, you have to get. And so what is happening, if you look at the cross section? This is always the coast, this is the sea surface, and the transport in a first 300 meters, 200 to 300 meters is from the coast toward the open sea. In order to not to lose the volume, we create the vertical flow toward the surface, and then here there is from the open sea toward the coast. So you have, there is, as a consequence of the Ekman transport from the coast toward the open sea, there is a creation of the circular movement where next to the coast there is an upwelling, the upward motion of the water masses due to this Ekman transport from the coast along the western coast of the. Why western coast? Because if we are talking about the eastern coast, and we have again the flow from north to south, then there will be the Ekman transport will be toward the coast, so there will be no upwelling. We'll see later why upwelling is an important process. And here it says also that the upwelling water along the west coast of continents modifies the weather along the west coast, but not only the weather, it also changes the equilibrium, biological and ecosystem equilibrium within the water column. Why? Because as we have seen before, when we were talking about the vertical convection, the vertical mixing or the transport of deeper water means the transport of water rich in nutrients into the surface layer and helping the phytoplankton to bloom, giving the food to phytoplankton. So that means that the areas where there is upwelling, which are the western coast, where the wind is blowing parallel to the coast in the northern hemisphere toward the equator, these are areas which are very, very productive, where the phytoplankton grows. And what that means that not only phytoplankton but zooplankton and fishes, all of them, they are present there because there is a stronger biological activity in that area. So if we find the areas where there is the coastal upwelling, these are areas very rich in fish, in biological productivity. So this is important. Why it influences the weather? it influences the weather, because bringing the cold water from deeper layers, means also the bringing the cold water from deeper layers. And you are creating the different vertical stratification also within the atmosphere. Okay, and so the weather along the west coast can be colder than it is at the same latitude over the rest of the ocean, because of the presence of the cold water patches along the coast. And here is another thing, is the so-called Ekman pumping or Ekman suction. Ekman pumping or Ekman suction, as the name says, is the process which has Ekman pumping or Ekman suction is due to the spatial heterogeneity or spatial variations of the wind, which then produces the vertical movement at the open sea, because at the coast we have seen, due to the presence of the coast, there is a convergence or divergence. But we have also seen that at the open sea there is this convergence or divergence due to the variability, spatial variability of the wind field. So if we have the wind Ekman transport like this one here, we have in this area here we have the convergence. By having the convergence, this is the sea surface. By having the convergence, there is the vertical. There is the pumping of the water from the surface into the deeper layers. So this is the vertical, the Ekman pumping. The Ekman pumping is simply a process which is due to the spatial variability of the wind field and the pumping of water from the surface layer to deeper layers, which is the opposite process of the Ekman suction. Ekman suction means that there is the situation is like this one, that the Ekman transport here is larger than there, so there is a divergence here, and then there is the Ekman suction. So that means that the Ekman layer sucks the water from the deeper layers. So this you don't have to have the coast. You can the coast is one of the possibilities, but you can have also simply spatial variations of the wind field. There is a third process by which we can have the vertical upwelling, the upwelling, which is the so-called equatorial upwelling. What is happening along the equator? Along the equator, we know that there are easterlies blowing along the equator on both sides. If this is the equator, and the easterlies is blowing this way, right? And the Ekman transport is to the right-hand side, but the northern hemisphere is to the right-hand side with respect. Sorry, this is wrong. These are not easterlies. These are easterlies. Right, the wind's blowing from east. These are easterlies. I'm always thinking in terms of the oceanography, because meteorologists and oceanographers, for some reason, they are mixing east and west. Oceanographers say where the wind blows from. By meteorology, oceanographer, they say where the current goes. For the meteorologist, it is logical, because you feel the wind where it comes from. For the current, I don't know. But anyhow, it's different. And so what is happening along this is the equator, and the northern hemisphere, just north of the equator, the Ekman transport is this way. In the southern hemisphere, the Ekman transport is to the left of the wind. And so along the equator, due to the different orientation of the Ekman transport, there is divergence in the equatorial area, and there is the equatorial upwelling. Is the upwelling due to the divergence, which is simply caused by the change of the sign of the Coriolis parameter. Okay, but when we see the exact expression for the Ekman layer and Ekman transport, we'll see how they are. Okay. So now we'll be talking about this second stationary solution of the equations of motion. First, as you may remember, was the geostrophic flow. Here we are looking at the steady homogeneous horizontal flow with friction on a rotating Earth. So, with respect to the geostrophy, there is the steadiness is present here as well as in a geostrophy. We have the Coriolis force as well as in geostrophy. The only difference is in this term here, which is the vertical eddy viscosity. So it's the viscosity of the water column. What is important here to note is that in the equations of the Ekman flow, there is no pressure gradient. Pressure gradient doesn't play an important role, as a different to the geostrophy. But what comes into the play is the friction. How can we interpret this? In terms of the vertical distribution of the flow within the water column? Within the water column, in that way we can distinguish two important layers or two important areas. One is this one here, where the friction plays an important role. And the other one, this is the first 300-400 meters close to the surface. Then if you go further deep, the friction is not so important, but what becomes important is the horizontal pressure gradient. Therefore, below this surface friction layer or the Ekman layer, this term becomes less important than the horizontal pressure gradient. So we have the surface Ekman layer. We have below, about 300-400 meters in the ocean, we have the interior layer where the geostrophy is present and important. And then we have again the bottom Ekman layer. So we have essentially three parts of the water column where different parts of the equations of motion are good approximation of whatever is happening there. So okay, so this is these are the first approximation, the eddy viscosity terms, which are where AZ and AZ are the constant eddy viscosity constant. And so these are the equations, and here is the F Coriolis parameter. Do you know that? And so this is easy to solve these equations, and these are the solution of the equation where we have, as a function of a depth, we have the V naught is the velocity at the very surface, and we have this amplitude decays exponentially with depth, and also is multiplied by cosine or sine, so it turns if you go deeper. So essentially we have the exponential decay of the exponential reduction of this surface wind-induced speed with depth. And here are the we can see that V naught is T is associated to the wind stress, and here is the constant. This constant alpha is obtained as F as a function of F and 2AZ. Let's go and see how. Now let's see the form of solution. At the C surface with Z equals 0, exponent of Z equals 0 is 1. So we have the C surface velocity. This is the boundary surface wind-induced velocity. This is the expression for it, and which really says what we have seen before in a very important concept as far as the wind is concerned, that the C surface wind-induced velocity is 45 degrees with respect to the wind, or 45 degrees to the right, 45 degrees when looking down into the northern hemisphere, or 45 degrees to the left-hand side in the southern hemisphere, and this is the magnitude of the velocity decays exponentially with depth. So it starts from V0, which is at the surface, and then exponentially decays, exponentially reduces with depth. So this is how the solution looks like what is the solution for the Ekman layer. It was interesting how experimentally this has been noticed, that the surface flow is not in the direction of the wind. When the people were doing the expedition in the northern, in the ice-covered areas where they were looking movements of the icebergs, and what they noticed that although the wind was blowing in one direction, the iceberg didn't move downwind, but they moved with a certain angle with respect to the wind. So this is the first time this thing was observed, that the icebergs did not move parallel to the wind blowing, and this is also a very simple explanation for it. But you know that icebergs are only 10% are out of water, and 90% is below the water. So icebergs are really an integration of the flow below the surface, an integration of the flow below the surface, which, as we can see here, changes with which has decays, reduces with exponentially with depth, and not only that. And obviously, this solution has been obtained by doing all the series of assumptions, and which can be good or as good as bad, and has their limits, obviously. First of all is that Ekman assumption was that there is no boundary, and that this is valid away from the coast. This is very, very strong assumption. However, we know from experimental data the fact that the wind induces a current which is to the right-hand side with respect to the wind in the northern hemisphere functions rather well. Then we have a deep water, which is valid for the water depth higher than 200 meters. Why so? Because if you consider that the surface Ekman layer is on the order of 200 to 300 meters, it's important that there is no overlapping with the surface and bottom Ekman layer. If it's overlapping, then there is no the solution doesn't work. Then the third assumption is F-plane. What that F-plane means, F-plane, we didn't talk about this so far. F-plane means that F is constant, the Coriolis parameter is constant. So we don't have the movement along the along the north-south direction, we don't have a moment larger than or on the order of 100 kilometers. In that case, we can assume that Coriolis parameter is constant in the first approximation. Then there is a steady state. This is where the wind blows longer than a pendulum day, longer than 2 pi over f. But Ekman calculated also the time-dependent solution. Then, fifth assumption is A zeta is a function of U10 squared only. It is assumed to be independent of that. This is not a good assumption. The mixed layer may be thinner than the Ekman depth, and the AC will change rapidly at the bottom of the mixed layer, because mixing is a function of stability, because the stability determines the mixing. Mixing across a stable layer is much less than mixing through a layer of neutral stability, obviously. If the layer is vertically stable, the mixing is much weaker. More realistic profile for the coefficient of eddy viscosity as a function of depth change the shape of the calculated velocity profile. We reconsider the problem below, but we will not go into more details about that. Then finally, it's homogeneous density. This is probably good, except as it affects stability. So there is a vertically homogeneous layer. This can be a good approximation if we don't have the strong thermocline or pycnocline during the summer season in mid-latitude areas. Okay, so this is again these are the equation. Flow in the Ekman layer of the sea surface carries mass, obviously. For many reasons, we may want to know the total mass transported in the layer. And now we will go and calculate the mass transport due to the Ekman layer, due to the wind influence. The Ekman transport is defined as the integral of the Ekman velocity UE and VE from the surface to a depth d below the Ekman layer. So if you do the integral over the entire Ekman layer, we obtain the mass transport due to the wind influence. And so this is how we obtain this mass transport in the x direction and the mass transport in the y direction by integrating the Ekman velocity from surface to minus d, where minus d is the depth of the Ekman layer. And the transport has units kilogram per meter square per meter per second. It is the mass of water passing through a vertical plane 1 meter wide that is perpendicular to the transport, okay? And extending from the surface to depth minus d. So if you imagine a surface which is large 1 meter and goes down to the bottom of the Ekman layer, whatever passes through the surface, this is the Ekman transport. So these are we calculate this Ekman transport by integrating the equations the equations before, and so a few hundred meters below the surface, the Ekman velocity approaches to 0. And so we don't have to take into consideration whatever is happening at the bottom at the minus d. Therefore, thus mass transport is due only to wind stress at the sea surface. In a similar way, we can calculate the transport in the x direction to obtain the two components. So these are two components of the Ekman transport. So the Ekman transport is directly proportional to the components of the wind stress at the surface. Okay, so this is a very good, very simple and elegant solution, which tells you that the stronger is the wind stress, the stronger is the Ekman transport. So that the Ekman transport is proportional to the wind stress. Another thing what is interesting is that the Ekman transport in the component of the Ekman transport in the y direction is proportional to the wind in the x direction and vice versa. So this is exactly what we have obtained here on a very qualitative considerations, that the Ekman transport is to the right hand side of the northern hemisphere with respect to the wind. here is this thing, what it says. And in the hemisphere, the wind is to the north in the positive y direction, south wind. Then to the so forth. Well, okay. Okay, so the result which follows from here is follows from the assumption that friction is confined to a thin surface layer, that it is zero in the interior of the ocean, and that the current is in equilibrium with the wind, so that it is no longer accelerating. This is which comes from the equation, type of equation what we have. We have the steady state flow. We have no time dependent flow. So this is the most important and which we'll be using very much the Ekman transport in considering the convergence, divergence, formation of eddies in the ocean and so forth. What about how this vertical distribution of velocity looks like from starting from the equation, well, from the solution what we just have shown? The wind direction is, if the wind direction is this way, 45 degrees with respect to the wind direction to the right is in the northern hemisphere is the surface Ekman flow. Further we go down, there is the rotation of the wind-induced flow, and also the exponential reduction of this flow. So the current is not only rotating in a counterclockwise direction, going down with depth, but it also reducing its magnitude exponentially. So we finally we would arrive at a position where the wind-induced flow is in the opposite direction with respect to the surface flow, which is kind of a strange thing, but this what we obtained from the solution. And the Ekman layer depth is more or less defined as the depth where the flow changes direction 180 degrees with respect to the wind-induced surface flow. And this is how it looks like projected on the horizontal surface. And at 35 degrees north for 10 meters per second, you can see that the surface flow is on the order of is about 6 centimeters per second. So you see that that generally, but this is not the case only the wind-induced current. Generally, in the ocean, the currents are 1 order or 2 orders of magnitude smaller than the wind velocity. If we have wind velocity 2 orders of magnitude larger than the flow in the ocean, in general, if you have a typical velocity, wind velocity is 10 meters per second, and typical current velocity is 10 centimeters per second. So we are talking about the 2 orders of magnitude weaker flow, except in a very specific cases where the differences can be 1 order of magnitude difference, where for example, in the area of Gulf Stream, as we have seen before, the Gulf Stream has the velocity of the order of 1 meter per second. So only 1 order of magnitude smaller than the wind velocity. Okay, so there is one very useful number which is called Ekman number. It's non-dimensional number, which gives the ratio between the friction force and Coriolis force, and which gives us the importance between the two forces, and which helps us later on to make some approximation as far as the equations of motions are concerned. And this is if you do these the ratio between these two, the Ekman layer, we get this is the ratio between eddy viscosity constant, and F is Coriolis parameter, and D is the depth of the Ekman layer. So this is the Ekman number. Ekman layer depth. This is another important parameter, which is arbitrary. See, because the Ekman currents decrease exponentially with depth, but it was proposed by Ekman that the thickness of depth dE at which the current velocity is opposite, as I told you before, to the velocity at the surface, which occurs at the depth of dE, and we can calculate this simply from the solution, where the Ekman layer depth is proportional to the eddy viscosity constant, inversely proportional to the F, to Coriolis parameter. If the Coriolis parameter is 0, the Ekman layer depth is undefined, which is at the equator. So at the equator, the Ekman layer depth is undefined for this specific Ekman solution. We calculate the Ekman layer depth using this formula here. We obtain typical winds, and the depth of the Ekman layer varies from 45 to 300 meters. And here is again then the velocity changes from 2.5 to 1.1% of the wind, depending on the latitude. So these are the important aspects of the wind influence, which will be used for our further consideration as far as the wind response, as the response of the ocean to the wind influence is concerned, and using the typical winds, and the previous formula, we obtained this typical Ekman depth as a function of latitude at 15 degrees north. And 15 or 45 now doesn't make any difference whether north or south, and you can obtain these values, which are so. As I told you before, below this Ekman layer, there it starts the interior layer where the horizontal pressure gradient determines the current, where the geostrophy becomes important. Okay. Here is the sum. Now we know how the Ekman transport being at the right-hand side with respect to the wind direction, how it determines divergence or convergence. We know the average schematic distribution of the wind as a function of latitude. This is starting from the equator and going up north. So we have traits in this subtropical area. We have westerlies in a mid latitude, and we have again easterlies in high latitudes, in polar areas. This is the typical distribution of the wind. So, how this reflects to the ocean? This is another interesting thing. To what extent this kind of wind pattern, what causes in the ocean? Okay, if we have here trades blowing this direction here, and in the northern hemisphere the transport is to the right hand side with respect to the wind direction. So we have the transport northward for up to about 30 degrees north. And then in the mid latitudes where we have westerlies, we have the transport, southward transport. And so as a consequence of this, we have in this belt between about 45, we have the convergence. In the ocean, due to the Ekman transport, we have the convergence. So there is a convergence here, equivalent to this. We have a divergence in the area where we have meeting easterlies with westerlies. So we have the convergence and divergence in these two areas. What that means in terms of the shape of the sea surface height. If we have where is here? Let's see if we have the convergence due to the meeting trades and westerlies, we have the convergence. Due to this fact, we have the sea level is higher in the area where there is a convergence and lower where there is divergence. Obviously, a part of this this convergent water volume is compensated by the downward vertical movement. So, if you look at in a vertical cross section here, you will see how do I explain? Okay. If you look in the vertical cross section where you have the convergence, we have you have the convergence here, so you have the flow toward here, but partly this flow, this convergence is compensated by the downward flow, but not completely. Partly there is an extra volume which is accumulated there where there is a convergence. So as a consequence of that, we'll have the bump at the sea surface. We'll have the extra volume being there, and at the same time, what is here, the result of this thing here is that there is a downwelling. So there is the downward flow of the surface water. And so, for this kind of shape of the sea surface, which is this thing here, the interface, the isopycnal surfaces will be looking this way. Okay? Because you're pushing the surface water downward, and therefore you are deforming the isopycnals downward in this area where there is the convergence. So there is a sea surface bump, but then there is also this shape of the isopycnals. Okay. So, and similar opposite to this thing, when we have divergence, we'll have the valley in the surface, and you will have plot this thing here. If you have a divergence, so there is the sea surface will be looking like this, okay? And the interfaces will be looking like this. See? So there are two different patterns which are created both at the surface and the interfaces due to the divergence or convergence in the world ocean. And this is very important, and then in understanding the global ocean circulation. And this is this is something which is related to what I was talking to you before, but this is associated to rings, which we will be mentioning next lecture. Remember this thing, and now it's much more clear if you go. I hope I will find it. Okay, here it is. Here is how it looks like in a cross section. This thing here, you have trade winds and westerlies. You have in the Ekman layer, you have the convergence. There is the vertical downward flow in the center of this bump, and you have this shape of isopycnals in the interior. So by Ekman transport, not only that there is a deformation of the sea surface, is also deformation of the interfaces. Not only that, but for the deformation of the sea surface on the order of centimeters or tenths of centimeters on thousands of kilometers in the world ocean, The deformation of the isopycnas are of the order of hundreds of meters. And so these are very important in determining, once the deformation of the interfaces are created, there is also the creation of the vertical geostrophic shear, as we have seen before. The horizontal pressure gradient, which is formed due to the downwelling, creates the vertical shear, as you can see from here. Okay?
Yes.
Yeah.
I don't understand one thing in the text. It says that the converging Ekman transports driven by the phase drives a downward geostrophic flow.
Drives a downward geostrophic just below the Ekman layer, above the vertical. This one.
Yes, I don't understand why the downward flow can be, our downward flow can be geostrophic. Maybe.
No, downward, no. Downward geostrophic. No, that's not true.
Just below, not the.
Yes, in the interior.
It's
Right. No, geostrophic flow is always horizontal. There is no vertical component in the flow. Drives the flow in the interior, geostrophic flow in the interior, which is by definition is horizontal. It creates the vertical velocity, which are not geostrophic. Just whenever you have the vertical velocities, the flow is not geostrophic. And you can see that it creates the shear. This is the vertical shear. At the surface is the higher velocity, and if you go deeper. So this is how the ocean looks like. This is the surface frictional layer, the interior, geostrophic interior, and then not presented here, the bottom boundary layer or bottom Ekman layer. Okay, I will stop here, and we'll see each other on Monday. Good. Have a good lunch. Where do you eat? Here? In ICTP. Good. They cook well. You like it? No.